All right, all right, all right. So let me ask if anybody has any questions. Anything y'all would like to go over before we start? No? All right, so once again, what we're about to do is not on your exam tomorrow. All right. There's new information right here. If you guys want to keep working on your stuff, go ahead. No pressure. All right. But we're gonna jump into something new right now. All right. Get rid of that real quick. You some wasting some good space. All right. And all right. So suppose a certain species of bird thrives on a small island. Its population over the last few years is shown in the table, right? So you have the years going across, right? 2009, 10, all the way up to 2013. Then you have the bird populations, 800, 897, 992. It looks like it's going up, so that's good, right? The population can be estimated using the function P of t is equal to negative 0.3 t to the third power plus 97t plus 800, where P of t represents the bird population on the island t years after 2009. So we can use this model to estimate the maximum bird population and when it will occur. We can also use the model to predict when the bird population will disappear from the island in this section. We will examine functions that we can use to estimate and predict these types of changes. All right. This is going to be excellent right here. All right. So here are we starting off with, right? Starting off with the power function. All right. So we're going to be identifying power functions. In order to better understand the bird problem, we need to understand a specific type of function, a power function. So it's a function with a single term that is the product of a real number, a coefficient, and a variable raised to a fixed real number. All right. So a number that multiplies a variable raised to an exponent is known as a coefficient. All right. The number that's in front. So as an example, consider the function for area or volume, right? The function for area of a circle with radius r is area of the radius is equal to pi r squared. We know that, right? And the function for the volume of a sphere, right? Like a basketball or something, right? With radius r is volume of the radius is equal to 4/3 pi r cubed, right? Both of these are examples of power functions because they consist of a coefficient, so there's a number in front, pi, right? Or 4/3 pi, whatever, multiplied by a variable r and then raised to a certain exponent power, right? So that's a power function. Okay. I just want to generalize that a little bit. So power function, right? A power function is a function that can be represented in the form f of x is equal to kx to the p power, where k and p are real numbers, and k is known as the coefficient, right? It's the number in front. All right. All right. Some of y'all might be wondering about this, all right? So is f of x equal 2 to the x power a power function, right? No, it's not. So a power function contains a variable base raised to a fixed power. right? This function has a constant base raised to a variable power, right? So that's actually called an exponential function, right? Not a power function, okay?
Yeah, the like square
Mhm.
become powerful.
Exactly. Yeah.
Power that is very
The base, right, is the variable instead of the exponent. Yeah. So let me ask y'all this question right here, right? This example, identifying power functions, right? Which one of the following functions here are power functions? So we got f of x is equal to 1, which is a constant function. We got f of x is equal to x, which is an identity function. We got f of x is equal to x squared, which is a quadratic function. We got f of x is equal to x cubed, which is a quadratic function. I'm saying a cubic function. Sorry about that. And we have f of x is equal to 1 over x, which is a reciprocal function. F of x is equal to 1 over x squared, which is a reciprocal squared function. And we got f of x is equal to the square root of x, right? Which is a square root function. And f of x is equal to the cube root of x, which is a cube root function. So which of these are power functions? What do y'all think? The cube? Okay. That's the only one? Hmm? Which one? Okay. Okay. Quadratic. All right. That's it?
square.
Okay. That's it? All right. All right. Shocking answer. All right. They're all power functions. Every last one. All right. For the ones that don't look like power functions, all right? Like I'm a throw the reciprocal one under the bus for a second, right? It's 1 over x. It might not look like a power function, but you know I could rewrite this as x to the negative 1 power. Boom. That was a power function. You know? The same thing with these root ones right here. Like I'll take the square root one. I can rewrite this as x raised to the half power. Boom, it's a power function. All right. So they're actually all power functions right here. Yeah, fun little activity. How about this? Which one is a power function? I like that. I agree with that. All of them. Yep. All right. Let's keep it moving. This next topic is real important right here. I'm going to be talking about end behavior of power functions, all right? In general, end behavior is important, but for now, we're just going to talk about the end behavior of power functions, all right? So this graph down here, right? Shows the graph of f of x, which is x squared, g of x, which is x to the fourth power, that's the orange, right? And h of x, which is equal to the x to the sixth power, right? That's like the turquoise looking color, right? Which are all power functions with even positive integer powers. Notice that these graphs have similar shapes, very much like that of the quadratic function in our toolkit, right? However, as power increases, the graph flattens somewhat near the origin and becomes steeper away from the origin, right? So you see our original function, which is the turquoise, right? That's the x squared, right? You see how the power is increasing when it goes to like x to the fourth? It kind of gets a little bit more flat. It's still going in the same direction, but it's like more narrower, right? And then as the power increases even more, it just gets more narrower, a little bit more steeper on the bottom. Mhm. So that's what happens at higher powers.
Well, like that.
Good question. I don't know. When you do the tables, that's what happens. So yeah. Like if you used your calculator and then typed in the function and then went to the table of values, you can actually witness this happen in real time. Like you can see how the y values are changing, right? Like how it's flattening out as it's going up and stuff like that. You know? Or you can just look at the graph and tell.
They're
Either
gonna
one.
yeah,
Yeah.
get it.
Yeah.
So mental, like E, X to the power,
Hmm.
let's say it was one,
Hmm.
10.
Yeah.
Let's say it was 10,
Something crazy. Yeah, yeah.
place for you to get to
Yeah.
this point, to that point,
Yeah.
more straight
Right.
versus how dumb I get.
Yeah.
Every time it's like, okay, I'm 100. Now
Right.
I'm 100 and I need to get to 1,000.
Right.
How do I get
Yep.
there? I live go straight up.
Right. It's true.
Focus.
It's true, yeah. So you kind of got to like zoom out for them higher powers when you're doing it. Yeah. All right, so look, to describe the behavior as numbers become larger and larger, we use the idea of in what you call it, infinity. Sorry about that. The idea of infinity, right? I should know this because this is a car, right? So we use the symbol infinity for positive infinity and negative infinity for negative infinity. When we say that x approaches infinity, right, which can be symbolically written as x goes to infinity, we are describing a behavior. We are saying that x is increasing without bound, right? With the even power function, as the input increases or decreases without bound, the output values become very large, positive numbers. Equivalently, we could describe this behavior by saying that as x approaches positive or negative infinity, the f of x values increase without bound. In symbolic form, we write as x approaches positive or negative infinity, f of x is approaching infinity. All right, good stuff. To be honest with you, on the test, if this is a little like a little bit much to write out, right? I'll accept pictures for this. So like basically what they're trying to say, like if I was looking at x squared or x to the fourth or whatever, and I asked you what the end behavior is, right? We don't know what the graph looks like, but for sure what we know is that it's going to have something like this going on. That's what it's trying to say. As x is going to um positive infinity or negative infinity, the y values are going to infinity. That's the end behavior of x to an even power, right? Right. Well, we can't talk about even without talking about odd, right? Gotta make it fair. So this figure down here shows the graph for f of x is equal to x cubed, g of x is equal to x to the fifth, and h of x is equal to x to the seven, which are all power functions with odd whole number powers. So notice that these graphs look similar to the cubic function in our toolkit, right? Again, as the power increases, the graph flattens near the origin, right? So we flatten it out right here, right? And becomes steeper away, right, from the origin, right? So boom. All right. So basically, like it looks like this, and then as the power increases, it's kind of coming a little bit more like this, also flattening out. And then same game if it's a little complex to say, as x is going to positive infinity, right? The y value is going to infinity and x is going to negative infinity, the y value is going to negative infinity. I'll take like a graph picture, if you want to do something like this and then this. I get what that means, as end behavior. Or when in doubt, write it out in words. I'll take that too. You describe to me what's happening. I'll take that. All right, so these examples they illustrate that functions of the form f of x is equal to x to the n power reveal symmetry of one kind or another. First, in the first figure, right, we see that even functions of the form f of x is equal to x to the n, where n is even, are symmetric about the y-axis, right? So if you flip them over the y-axis, they look the same, like x squared, right? Flip it over the y-axis is the same thing, right? Um, in the last figure that we just looked at, we see that odd functions, right, like x cubed, that's the one that goes like that, right? Um, of the form f of x is equal to x to the n, where n is odd, are symmetric about the origin, right? So if we flip them over the origin, they come back to the way they are, right? So it goes up like this, right? So if we're flipping over the origin, we have to flip down, and then we have to flip around to X. That is right back to the same thing that we had before. It's a double flip for the origin, right? X and Y. Yeah. Okay. So for these odd power functions, as X approaches negative infinity, f of X decreases without bound. As X approaches positive infinity, f of X increases without bound. In symbolic form, we write as x goes to negative infinity, f of x is going to negative infinity. And as x goes to infinity, f of x goes to infinity. The behavior of the graph, the behavior of the graph of a function as the input values get very small. So as x is going to negative infinity, right? And get very large as x is going to infinity is referred to as the end behavior of the function, right? So we can use words or symbols to describe the end behavior. That's what I'm going to be asking you guys. I'm going to give you a function. I'm going to ask you, like, what does this function look like? Right? So what is the end behavior of it? And you're just going to tell me. All right. I'm making it a little bit more free for you guys in that, like, if you want to draw a picture, cool. Right? If you want to write it out in words and tell me, cool. Like whatever works for you. All right. If you want to use a symbolic notation, go ahead. I'll take that too. I feel like the picture is the easiest one though. This is what I'm saying, right? So in this figure, right, it shows the end behavior of the power functions of the form f of x is equal to k n to the x, where n is a non-negative integer depending on the power and the constant. So let's say that we have a positive k, right? So that means that's going to be x to the k power, right? For an even power, right, as x goes to negative infinity, right, f of x is going to infinity, and as x goes to infinity, f of x is going to infinity. So that's why we have these double arrows here. Negative infinity is to the left. The y values are going to infinity, right? Positive infinity is to the right. The y values are going to infinity. That's for even power, right? For an odd power, right? As x approaches negative infinity, f of x is going to negative infinity. So as we're going to the left, right? X is getting smaller, right? The graph is going to negative infinity, it's going down, right? And then on the flip side, right, as x is going to infinity, the x's are getting bigger, right? Where the y values is also going to infinity, right? So that's for an odd power. Think of x to the third power, odd. Think of x to the second power, that's even. Okay? Now, let's say that we had a negative k. Remember that these are going to be multiplied by some constant that we're calling k, right? So in this case, k is negative. So now this first graph here, think of y equals negative x squared, right? It's flipped over the x-axis, right? So this is what it looks like. So as x is going to negative infinity, right? The y value is going to negative infinity. And as x is going to positive infinity, the y values are going to negative infinity, right? This is when the graph is downward, right? So it's flipped, all right? The other side, right? This is odd now. Think of y equals negative x cubed, right? So this is going to be kind of like flipped over the y-axis, right? With the negative, flipped over the y-axis, all right? It should be the x-axis though. No, it is the x-axis. What am I talking about? It's the x-axis. Sorry about that. It's flipped over the x-axis, right? So now as x goes to negative infinity, right? The y values are going to infinity and x is going to positive infinity, right? The y values are going to negative infinity. All right. So it's kind of flipped a little bit. And these are like generic. Bless you, bless you. Bless you, bless you. Low-key, these will be the answers to like all your homework. It's either going to be even with k positive, right, or odd with k positive, or it's going to be negative with, when k is negative, it'd be even power or odd power. Mhm. Give y'all a little bit of tea. So given a power function, f of x equal to k n to the x power, where n is a positive integer, you want to identify the n behavior, right? So here's how we do it. Step one, determine whether the power is even or odd. That's simple. We just look at the exponent that's on it, right? Step two, determine whether the constant is positive or negative. Again, simple. That's just the coefficient that's in front of the variable, right? And then step three, use the figure four to identify the end behavior. So they're telling you to use these four charts right here to tell me what the end behavior would be. All right. And that's it.
So
Mhm.
it's going to add, positive and negative.
It does. Yeah. So if it's positive, if k is positive, this is what the even function looks like and the odd function, right? But if k is negative, this is what the even function looks like, and this is what the odd function looks like. Yeah. Mhm. Yeah. Right, right. That number doesn't matter. All we care about is the sign of it. Huh? Positive or negative. Yeah, right, right. Let's take a look at an example. What would the end behavior be of this? I have f of x is equal to x to the eighth power. What do you guys think? What's the end behavior gonna be? Hmm? Even and what? Is k positive or negative? It's positive, right? So this, I don't know what it's gonna look like, but I know it's gonna end like this, and it's gonna begin like this, right? You could say it just like that. Or you could say as x approaches negative infinity, f of x is going to infinity, right? let me see it like that, going to infinity. Or, and as x approaches positive infinity, f of x approaches infinity. However you want to give it to me, I'll take either one. If you're not sure what to do, write it in words. Just tell me that. I'll accept that. So the negative from where? From going to negative infinity? Yeah, because like that's all the numbers that are on the left. Yeah. And then all the numbers that are on the right. This is your left and right. I'm sorry. So that's all the numbers that are on the left, right? That's the negative infinity. All the numbers on the right now, right? That's the positive infinity. Yeah. So the top portion like this would be negative infinity, and then the bottom portion is positive infinity. This is positive infinity. So that's like this part here, and this is that part, if that makes sense. It's good. If you're doubting it, just write it in words. Don't even stress it.
I can see.
Yeah. Yeah.
Only when they add negative, then it's inverted. We out
Right. Yeah.
of there. Yeah, possible.
Right. It's positive and even.
But the negative.
Oh, because it's the left-hand side, like the negative numbers. Yeah, yeah, yeah.
But at the end, it's sometimes it's positive.
Yeah. So it looks like this first one. That's what I'm trying to describe, because x is to the eighth power, so the eight is even, right? And the number in front of the x to the eighth power is positive. So that's why.
Well, actually, what is just actually better by the head. The
Mhm.
function of x is approaching the positive side.
It's approaching both left and right. So that's why I have to separate them. Like, what is it doing on the right hand side? What is it on the left hand side? Yeah. Well, like I said, whatever is easiest for you. If you want to give me a picture, cool. If you want to write it out like that, cool. If you don't know what to do, just write in words. I'll take that too. I feel like the picture is good enough though. That's my opinion.
Like going, well,
Yeah.
that's, uh, even power on, yeah. That,
I even take that too. I'll even take that too.
that first I wasn't getting, I'm like, wait,
Yeah.
the x is negative,
Mm-hmm.
the graph goes down, you're always getting multiplied by a negative number.
Right.
So
Right.
negative seven to the third power, even though negative seven times negative seven is positive,
Mm-hmm.
it needs to get multiplied by
Right.
negative seven.
He's gonna put it down. Yeah. What about this? What do you guys think is the answer for this one?
So pushing that.
The negative, right? So what's the end behavior? Tell me. Wait, hold on. I gotta get my pen. All right, go ahead. Okay. So like up here and down here?
Yes.
All right, good. That's it. All right. So you could also say as x goes to negative infinity, f of x is, I keep making that mistake, goes to infinity, right? Plus as x goes to positive infinity, f of x goes to negative infinity. I'll take either one of those answers. It doesn't matter. All right. So this one, x goes to negative infinity, f of x is going to infinity. That's this part here. All right. And then This one, as x goes to infinity, f of x goes to negative infinity. That's this part here. All right. Questions on it? Make sense? All right. Yeah, this is odd. Oh, positive, like a positive odd number. Okay. Yeah, yeah. So if I had like, um, yeah, x to like the third, or even like x to the fifth, you know, say I had f of x equal to x to the fifth power, right? So then I don't know exactly what that looks like, but it looks something like this. All right. So the end behavior, would be positive, positive, and negative, negative. Right. So this one as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, right? F of x goes to negative infinity. All right. For example, make sense? Well, mhm. Not in the even one. I'll show you. So that's this one. The second one right here. So we good? All right, analysis. So we can check our work by using a table feature on a graphing calculator. So this part you could do in a graphing calculator. You can get the table of values for the x and for the f of x. All right. So we can see from table 2 that when we substitute very small numbers for x, the output is very large. And when we substitute very large values for x, the output is very small, meaning that it is a very large negative value. Okay. What's the end behavior of this? Hmm? It's gonna go down, right? Right. Mhm. So like this. Oh shoot. Let me get my pen. All right. Let's see. Questions on this? Anybody? Okay. And now we're gonna do identifying power functions, right? So as oil pipelines burst in the Gulf of Mexico, causing an oil slick in a roughly, excuse me, circular shape, the slick is currently 24 miles in radius. Yikes. But that radius is increasing by 8 miles each week, right? You want to write a formula for the area covered by the oil slick by combining two functions. The radius r of the spill depends on the number of weeks that have passed. This relationship is linear, all right? So we have r of w, which is the radius of the, what was w again? The week, excuse me, is equal to 24 plus 8w, which is w's per week, right? So we can combine this with the formula for area, which is pi r squared, right? Area of a circle, composing them together, right? These functions gives us a formula for the area in terms of weeks. So area of weeks is equal to area of the radius per week, right? So just kind of plug it in, area times the 24 plus 8, and then plug that into the area for the circle. So pi 24 plus 8w squared. Yeah. Questions on that? Yeah. And when you expand it, you get that. All right, this formula is an example of a polynomial function. A polynomial function consists of either zero or the sum of a finite number of non-zero terms, each of which is a product of a number called the coefficient of the term, and a variable raised to a non-negative in integer power, right? Mm-hmm. That's possible too. So let n be a non-negative integer. A polynomial function is a function that can be written in this form. F of x is equal to a sub n, x to the n, plus a sub n plus 1, n minus 1, excuse me, raised to times x raised to the n minus 1 power. So on and so forth, so you get to a to the 0, right? This is called the general form of a polynomial function, right? Each a1 is a coefficient. It can be read, right? It can be any real number, sorry. If a sub n does not equal 0, each product a sub I x to the I is a team is a team of a polynomial function. All right.
What are they again?
As long as you could expand it like this, you're good. This one we want to sketch the graph. So what do I know? I have a 0 at x equals 1, a 0 at x equals -3, right? And this is going to be what power? 4 and 4 is 8, right? So I don't know exactly what this is going to look like, right? I'm kind of just making this up as I go. But let's say that that's 1. And let's say that this is 1, 2, 3, -3, right? I don't know what this will look like, but I feel like it's going to be something like this. Reason for that, x minus 1 to the fourth power, x plus 3 to the third power, plus someone else who's solo in the front. 4 plus 3, 7 plus 1, 8. So it's even. So I think the graph would look like that. Is it 100% right? No. It's going to look something like that. Questions on it? Okay.
First extra next to the 1/4.
Mm-hmm.
I feel I make the solution for x minus 1 to the fourth power and x equals to the cube.
Uh-huh.
So I just should that x is the answer to that.
You don't have to expand it if you don't want to, but yes, you could expand it and rewrite it as the original if you wanted to. Which one? Downward. So that's like when it has a negative power in the front. Yeah. So if it was like -1/4, then like that, yeah. So identifying the degree and leading coefficient of a polynomial function, right? Because of the form of a polynomial function, we can see an infinite variety in the number of terms and the power of variable. Although the order of the terms in the polynomial function is not important to perform operations, we typically arrange the terms in descending order of the power or in general form. The degree of the polynomial is the highest power of the variable that occurs in the polynomial. So it is the power of the first variable in the function if a function is in general form. The leading term is a term containing the highest power or the variable or the term with the highest degrees. The leading coefficient is the coefficient of the lending team. Leading team. Sorry, leading team. It's the number that's in front of it. Just to kind of give you a picture about what I'm saying. All right. Technology of polynomial functions. We often rearrange polynomials so that the powers are decent. When a polynomial is written in this way, we say that it is a general form. All right, so f of x is equal to a times x to the n, right? So the a is a leading coefficient. The degree is the n on the x, and it can be written as the series leading term. When a polynomial is written in this way, we say that it is in general form. All right. Little t. So given a polynomial function, identify the degree and leading coefficient. Step one, that's how you do it. Find the highest power of x to determine the degree of the function. Step two, identify the term containing the highest power of x to follow as the leading term. Or step three, identify the coefficient of the last standing. All right? So your choice. You guys try. All right, f of x. All right. What is the degree, the leading term, and the leading coefficient?
Zero, the negative is zero, x to the third. Negative four.
So -4 x to the third, that's a term. All right. What's the coefficient?
Three.
Uh, the -4, right? The number that's outside. Okay. And what about the coefficient? You know. All right. So I guess we're done with that one. What about g of t? Mm-hmm. Okay. What's the coefficient? Good. Just a 5. Oh, it's a 2 on top. All right. That's it. H of P. Good. Sure. That's good. And then what is the power? The exponent. What is that? 3. Right? The second g of t. Okay. Oh, it's 5. Sorry, I didn't see that. That's my fault. Oh, wrong color. That is my fault. Let's look more closely at that. Okay. Mm-hmm. You're welcome. You're welcome. All right. I'll leave this for you guys to try while I get some water back. All right. What is the highest degree power here? Very good. What is the leading term? Negative x to the 6. Good. What is the leading coefficient? Good. And that's it. Questions on this? Not bad, right? Most of your homework is this topic. So now we're gonna be, hold on. Identifying End behavior of polynomial functions. So knowing the degree of a polynomial function is useful in helping us predict its end behavior. To determine its end behavior, you look at the leading term of the polynomial function, because the power of the leading term is the highest that the term will grow significantly faster than the other terms as x gets very large or very small. So its behavior will dominate the graph, right? For any polynomial, the end behavior of the polynomial will match the end behavior of the term of the highest degree. All right. I just want to show you a couple examples real quick.
Putting what,
Uh-huh.
with the multiple as multiple.
Yeah. So here, polynomial function, right? Got this huge thing, f of x equals 5x to the 4 plus 2x cubed minus x minus 4, cool, right? The leading term is 5x to the 4th power, right? So what do we know? We know that the coefficient in front is positive, and we know it's being raised to an even power. So essentially, we know that the end behavior is going to be positive. It's going up. That's my end behavior right there. All right. Not asking you to graph it. I'm just proving to you that, like when you look at the leading term, that's going to be the end behavior. That's all. All right. Let's look at another example real quick. So over here, I have this polynomial f of x is equal to negative 2x to the 6 minus x to the 5th plus 3x to the 4th plus x to the 3rd, right? My leading term is negative 2x to the 6. So we already know that's an even power. So we're going to have one of those like double infinities or double negative infinities, right? But because the number in front is negative, it's going to be down. This is what the actual graph looks like, right? But I'm just telling you this to prove that the end behavior will be going downwards. All right. Just wanted to make that clear. So, right? Yeah. Let me show you another one real quick. Huh? That's tomorrow. Yeah, everybody voted for tomorrow. Oh, no, you good, you good. I was thinking like if anybody like wants to pop out early tomorrow, y'all could come in early and start early if you want. Up to you, no pressure. Right? I don't. Huh?
After the exam is done.
Yeah, you can leave.
Oh.
Yeah.
I know that.
Yeah, yeah. Huh? Say it again? Justification of powers? No, 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 no. No. We're doing end behavior. Yeah. 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 I don't think we got there yet. Yeah, but we getting there. We getting there. We're building up to it. Yeah. Yeah. Hi.
Did you decide 30 minutes? Have the whole time?
Yeah, the whole time. Yeah. All right, so here's another one, right? I have this polynomial. F of x equals 3x to the 5th minus 4x to the 4th plus 2x squared plus 1, right? Blah, blah, blah. The leading term is 3x to the 5th power, right? So what do I know about that? The coefficient in front is positive and the power is odd. So I know that the end behavior is going to be like this. Huh? Hold on, I gotta bear with me one second. I gotta switch this up. I need my yellow back, man. I don't know. I feel like yellow pops a little bit better. I'm gonna switch it up to yellow. All right. want to show y'all another one. And when you guys are going through the recording, if you want to like pause it and then take pictures of this, y'all can go ahead and do that. So here goes another polynomial. I have f of x is equal to negative 6x to the third power plus 7x squared plus 3x plus 1. My leading term is negative 6x cubed, right? So what do I know about that? The coefficient number in front is negative. So you already know what's going to happen. We're going to flip it, right? And then also it's odd, right? So I know that my end behavior, right? Oops. Let's see. I don't know. I like the yellow better. What y'all think? I like the yellow better than the green. But yeah, so that's gonna be the end behavior right there. All right. And that's it. Mhm. So usually, since it's blue, let's say that I had f of x is equal to x cubed, right? So x cubed looks like this, right? But because the number in front of the one that we just did was negative, right? It flips, right? See, I kind of like flips over the x-axis a little bit. So that like that's what I mean by the negative. Yeah. It's still a odd powered function though. It's just flipped over the x-axis. Do a what? So I don't know, sometime after the final. Let's just say the 31st of July. Yeah. Yeah. Uh, just give me 100. That's all. And it's okay if you want to like try the homework and you get it wrong and then try it again. Like, nope, no, I don't care about that. I'm not looking at that. All right. Hmm. Matter of fact, if y'all want to see what I'm looking at, I'll show you in a second. Okay. Sorry about that. I was getting a little frozen. So identifying end behavior and behavior of polynomial functions, right? So describe the end behavior and determine the possible degree of the polynomial function. Okay?
Professor, in the exam tomorrow,
Yeah.
you're gonna do coordinate formula, right?
Which one?
Coordinate.
Yeah, that'll be there. Yeah, that'll be there. So it's on your formula sheet. So kind of know what the end behavior would already be because we have the graph, right? But describe it to me. You can use words, you don't gotta use symbols. So it's odd, right? So as x is going to negative infinity, right? Well, no, the f of x is going to negative infinity as well, right? And as x is going to positive infinity is increasing, right? The y values are increasing. That's it. That's all you have to tell me. It increases. So as x is as x is increasing going to the right, the graph is going up, positive infinity. And as x is going to the left, to negative infinity, it's like the graph is going down. Yeah. Basically, in this question, I know you could kind of tell what it is just by looking at it. I'm asking you to just tell me in words. You know, if you want to use mathematical symbols, go ahead. No pressure. All right. It'll be on your test, yeah. Test 2. Yeah, I'm fine with that. Or symbols. Or you can draw it. Right? Like if I give you a function and you want to just draw it, I'll take that too. You know? Yeah.
That's the graph of the polynomial.
Yeah. Yeah. Mm-hmm. We'll take a look. You'll see. So describe this one to me. The end behavior. Even and negative. Good. So as x is going to negative infinity, the y values are no negative, and as x is going to positive infinity, the y values are infinity. That's it. How you'd write it if you could describe it to me in words like how you did right now. But if you want to do like the math notation, this is the math notation, right? As x approaches negative infinity, f of x approaches negative infinity. And as x approaches positive infinity, f of x approaches negative infinity. And that's it. Yeah. Either way is whatever works for you, no pressure. Mhm. Are you seeing like a question like this now? That ever unfreezes? So given the function f of x is equal to negative 3x squared times x minus 1 times x plus 4, express the function as a polynomial in general form, right? And determine the leading term, degree, and end behavior, right? So, okay. I don't feel like multiplying this out because I know y'all know how to do that already. So I'm not gonna even ask y'all to do that, right? But what would the leading term be? We might actually have to multiply it out to get the leading term. Damn. All right, let's do it real quick. So f of x is equal to, I would do the binomials first, right? So 3x squared, that's negative 3x squared, times what's this? X squared plus 4x minus x minus 4, negative 3x squared, x squared plus 3x minus 4. Distribute this in. What do I have? Negative 3x to the fourth minus 9x cubed plus 12x squared, right? Not too bad. All right. What's the leading term? A negative negative is a positive, yeah. Yeah. So you said negative, perfect, right? That's my leading term. And what's the degree on it? The degree is 4. Very good. And the end behavior. Even and negative. Good. Yeah. So I would take an answer that looks like this if you want. You could draw it out if you want. If you want, you could tell me in symbols, right? As x approaches negative infinity, right? F of x is going to approach negative infinity. And as x approaches positive infinity, f of x approaches negative infinity, right? However you want to do it, no pressure. All right. I personally like the I like the drawing. I'm cool with that. All right. If you want to give it to me like this, go ahead. If you blank out on the test, just write it out in words. You know? Yeah, go ahead. No, you're fine. Hmm.
And behavior. So you don't have the rest of this graph, so it's okay if you don't have.
Yeah, I don't need you to draw the whole graph. I'm just asking about what the end behavior is. Like, what is it doing? Mhm.
That we
Because it's an even power function, right? It's going to be going down like that. Yeah. If it was an odd power function, it's like one is going up, one is going down kind of situation. Right. So we good? All right, let's take a look at something else. Doo, doo, doo. Let's look at this test question real quick. Uh-huh. Let's y'all try it. So given a function f of x is equal to 0.2 times x minus 2 times x plus 1 times x minus 5, express the function as a polynomial in general form and determine the leading term, the degree, and the end behavior of this function. All right. I like how the homework has this section really organized very well. So tomorrow, tutoring opens up at 1 o'clock. So if you guys want to come in early, go to tutoring, that's fine. You know, you guys have all the homework. That's what's going to be on the test. All right. While I would love for you guys to finish everything before tomorrow, if time is against you, at least try and touch every single like topic, like all the homework topics, just so that you could at least say like, all right, I'm familiar with what's gonna be on it. As you can see with the homework though, right? Like once you know how to do one, the rest of it just like flows. It's the same concept again and again and again. Yesterday's lesson. Yeah. Today don't count. This is test two. Test two, yeah. This is next week, Thursday. Yeah. Yeah. Y'all got the videos, y'all got the homework. That'll be good. Oh, tomorrow, bring y'all calculators. All right. If you can print out the formula sheets, I'm gonna try and print them out for you, but if you can print them out and bring them, all right. The formula sheets. Yeah. They're on Brightspace. Yeah. You don't need the web work one. That's not really gonna help you. I'm talking about like the algebra one. Yeah. All right. Let's look at this one, right? So we want to express this function as a polynomial in general form, right? So let's do that out. It's the sucky part. So I have hold on, I gotta get my pen. Let me get my pen. Can't believe I came to the problem without a pen. You believe that? All right, so I have f of x, right? Is equal to, I'm gonna hold on to that 0.2. Let me multiply this out, right? So this is gonna be what? X squared minus x minus 2 times x minus 5, right? Let's keep it going. I have 0.2 I'm gonna multiply this part out. This is gonna be x cubed minus 5x squared minus x squared. What's that? Plus 5x plus 10. Combine like terms. 0.2. I'm missing 2x. I am missing 2x. Where's 2x supposed to be? Hold up. Let me see if I get it back. X squared, negative x squared. Positive 5x. Yeah, negative 2x. Yeah. Plus 10, right? That's it. Okay, combine like terms. I have negative 6x squared. What's that? Plus 3x plus 10. Very good. Now, oh boy, here we go. Distribute this out. 0.2x cubed. Oh Lord. What's this gonna be? 1.2? Appreciate it. Squared plus, oh Lord, what's this next one? 0.6x. And what's this last thing? Plus 12? 2? Okay. All right. Bam. All right. So what's my leading term here? Very good. What is the degree, the leading degree?
3.
3. All right. Tell me about the end behavior. Good. All right. So it's going to be
X when X approximately
mhm,
of X is
right.
X
Approach negative 50.
is negative.
Correct. Correct. All right. So this is it right here. All right. I personally like the pictures, but if y'all wanna use the symbols, go ahead. All right. Yeah. That's it. Questions on this?
What's the term? Positive?
The coefficient. So you see the 0.2 in front? How it's positive? That's why. Yeah. 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 All right, all right. All right, so obviously you could probably guess that keep talking about the end behavior, right? But what happened in the middle? All right, I can't even draw this. What happens in the middle? Let's talk about that. All right. We call that local behavior. Oh Lord. All right. So in addition to the end behavior of polynomial functions, we also are interested in what happens in the middle of the function, right? In particular, we're interested in locations where the graph behavior changes, right? That's the key. So a turning point is a point at which a function value changes from increasing to decreasing, excuse me, or decreasing to increasing, all right? We are also interested in the intercepts, all right? As with all functions, the y-intercept is the point at which the graph intersects the vertical axis, right? The y-axis, right? The point corresponding to the coordinate pair in which the input value is 0, blah, blah, blah. When you have a function and you plug in x equals 0, that number that you get out at the end, that's the y-intercept, period. All right? Where was I? Okay. Because a polynomial is a function, only one output value corresponds to each input value. So there can only be one intercept. There's only one y-intercept. Just so we clear about that. Not 3, not 8. There's one y-intercept, all right? The x-intercepts occur at input values that correspond to the output value of 0 when you set the whole equation equal to 0, right? It is possible to have more than one x-intercept, all right? Just to show y'all, oh shoot. Here we are. So we have this graph right here, right? So you see at the very top right here, this is a turning point, right? And on the x-axis, these 3 points, let me highlight them. These 3 points right here, these are my x-intercepts. They are also solutions to the equation, all right? They're also solutions to the equation. And then up here at the top, we got the turning points. That's what's happening in the middle, all right? Now, just because I like math, I'm gonna mention the word turning point, right? But I'm not actually gonna tell y'all how to get the turning point, all right? Y'all gotta wait for calculus to see that, all right? Just know it exists though. Huh? Yeah. Which derivative? The first or the second? You gonna see. You gonna see. You gonna see. dy over dx. Yeah.
Wow.
Yeah. You'll get there. Don't worry. You'll get there. All right. So intercepts and turning points of polynomial functions. So a turning point of a graph is a point at which the graph changes direction from increasing, decreasing, or decreasing to increasing. The y-intercept is the point at which the function has an input value of 0. The x-intercepts are the points at which the output value is 0. All right. Nothing new here. Well, we kind of knew this already, except for the whole turning point thing. And y'all know I gotta hook y'all up with some tea, right? Give y'all a little how-to right here. All right, so given a polynomial function, we want to determine the intercepts, right? This is how you do it. Step 1, determine the y-intercept by setting x equal to 0 and finding the corresponding output value, right? Determine the x-intercepts by solving for the input value that yields an output value of 0. Simple, right? Not too bad. So let's look at this. Determining the intercepts of a polynomial function. So given the polynomial function f of x is equal to x minus 2 times x plus 1 times x minus 4, written in factored form for your convenience, determine the y and the x-intercepts. Oh, shoot. It's going to be nice right here. It's going to be nice. Which one you guys want to do first, the y-intercept or the x-intercepts? The x-intercepts? All right, let's do the x-intercepts, right? So for the x-intercepts, how do I get that, right? I want to set the whole equation equal to 0, right? So I'm going to have, hold on, I got to get my pen. I always do this. I forget to bring my pen to the problem, you know? All right, we're gonna go with purple this time, right? So 0 is equal to x minus 2 times x plus 1 times x minus 4, right? And it's as simple as you might think. Set each of them equal to 0, right? So x minus 2 equals 0, add 2, right? So x equals 2, right? x1 equals 2, let's say like that. X plus 1 equals 0, subtract 1, subtract 1. So x2 is equal to, like, let's say -1. X minus 4 equals 0, add 4, So I have x3 is equal to 4. Boom, right? These are my x-intercepts right here, right? Technically speaking, x-intercept is not a coordinate, it's a point, right? So what are the points? What are the points? Like, what's this first point here? 2, 2 comma 0. Very good. What about the second one? -1 comma 0, right? What's the last one? Perfect. What's the y-intercept? How do I do that?
X also remember.
Right. So I want to find f of 0 to get the y-intercept. So that's going to be what? 0 minus 2 times 0 plus 1 times 0 minus 4. All right. That's going to be what? -2 times 1, right? Times -4. What's the answer? Good. All right. So what's my y-intercept? Because remember it's a point, right? So what's the point going to be?
0.8.
0 comma 8. Very good. And that's it. All right. That's literally the rest of your homework. Very, very good.
And,
Yeah. Not asking you to graph it, just asking you to find the intercepts, right? All right, talk to me now. How we do this? Same thing. I want the x-intercepts, I want the y-intercepts. I have f of x is equal to x to the 4th power minus 4x squared minus 45. You want to do the x-intercepts first? All right, let's do that. So, no, x-intercepts 0 equals x to the 4th, right? Minus 4x squared minus 45, right? All right. So let's factor this. How we factor this? Huh?
X squared.
Uh-huh.
X minus
Mhm.
45, then try to.
Okay. So we actually skipped this in 28. But what you do, right? You want to set x equal to, let's say, x squared, right? So you can rewrite this as x squared minus 4, right, times x. Let me just call this x. Let me not confuse y'all. Times x minus 45. Factor it the way you normally would, right? So this is what? 9 and 5, I think. So x minus 9, x plus 5. Something like that, right? Now substitute back x squared in for x. So this becomes what? X squared minus 9 times x squared plus 5. That's the difference of two perfect squares right there. Factor that out. So we have x minus 3, x plus 3, x squared plus 5, right? Now we back to what we had before, right? Set all of them equal to 0, all right? Why are you not writing? All right, here we go. So I got x minus 3 equals 0, add 3, add 3. I got x1 is equal to 3. I got x plus 3 equals 0, subtract 3, subtract 3. So I have x2 is equal to -3. I got x squared plus 5 equals 0, subtract 5, subtract 5. So I have x squared is equal to -5, right? What do I do after that? Square root it, right? Then we're going to have x is equal to some kind of imaginary thing, right? So how many real numbers do I have, right? X-intercepts, what are they? 3, 0, and then -3, 0, right? All right, y-intercept now. I don't know if you guys can tell what the y-intercept would be just by looking at it.
So,
It is, right? So it would be what? 0, comma, negative 45, right? So how did we do that? We just found f of 0. We really just plugged in 0. So this became like 0 to the fourth minus 4 times 0 to the second minus 45, which is just 0 plus 0 minus 45, which is the negative 45. That's how we got that. Okay. Questions on this? So y-intercept, just plug in 0, x-intercept, factor it, and then set all the factors equal to 0. All right. If you get down to a quadratic, you already know y'all got the quadratic formula. Y'all got, huh? Yeah. Yeah. This substitution thing though, like we skipped it in 28, so you might not have seen it. Some people might have seen it, some people might have seen it. Yeah. I personally skipped it. I don't know about other people. Yeah. Yeah. I got you. Yeah. But like that same factoring thing that we did back then, it comes back, the whole like four terms, factor by grouping, all of that is still relevant here. Mhm. All right. That was smooth. That was smooth. Let's try another one. A little bit harder. This is odd. So I just want the y-intercepts and I want the x-intercepts. All right. So which one do we want to do first? X-intercepts. All right. So we're going to set this equal to 0. All right. So I want to factor this. What should I do first to factor this? What is it? Yes. Greatest common factor, right? So I got 2x. And what's left over? I got x squared minus 3x minus 10. All right. Let's keep going with this. I got 2x. What's this? X minus 5, x plus 2. All right. Y'all got the formula sheet, so y'all could, if y'all didn't see how to do that, y'all could just use a quadratic formula or something to get that. All right. Anyway, what's my x-intercepts? So I got 2x equals 0. So x1 equals 0. X minus 5 equals 0. Add 5, add 5. So I have x2 equals 5. X plus 2 equals 0. Subtract 2, subtract 2. So I got x3 is equal to negative 2. Give me the points real quick. So I got 0, 0. Perfect. And what else I got? 5, 0. Very good. And what else? Negative 2, 0. Perfect, perfect, perfect. What's my y-intercept? So remember how we do that? We're going to do f of 0, right? So we're just plugging in 0. So I got 2 times 0 cubed, 6 times 0 squared, minus 20 times 0. All right, so it's 0, all right? So give me the coordinate for the y-intercept. Very good. And that's it. Okay. Questions on that? Yeah, it's possible to also have it pass through the origin like that and be an x-intercept and a y-intercept at the same time. So we good? I don't think I gave you any questions that hard on the test. I mean on the homework. And definitely not on the test. That's way too hard. All right. Which one? X
That's -20.
up top here, minus 20x. Oh, you mean over here? Times 0. Yeah, because I'm plugging in 0 for all the x's there. Yeah. It's about to get lit right here. We're going to be comparing smooth and continuous graphs now, right? So the degree of a polynomial function helps us determine the number of x-intercepts and the number of turning points, all right? A polynomial function of nth degree is the product of n factors, right? So it will have at most n roots or zeros or x-intercepts, all right? The graph of a polynomial function of degree n has at most n minus 1 turning points, all right? So this means that the graph has at most one fewer turning point than the degree of the polynomial, or one fewer than the number of factors. Excuse me. A continuous function has no breaks in its graph, right? The graph can be drawn without lifting your pen from the paper. A smooth curve is a graph that has no sharp corners, right? The turning point of a smooth graph must always occur at rounded curves, right? So it's gonna be smooth, you know? The graph of polynomial functions are both continuous and smooth, right? I put that face there because that sounded a little complicated. Mhm. All polynomial functions are both continuous and smooth. Yeah. Yeah. So intercepts and turning points of polynomials, right? So a polynomial of degree n will have at most x-intercepts and n minus 1 turning points. All right. So if the leading term is to the 9th power, that means that it could have at most 9, right, intercepts, right? Doesn't mean it will have 9, it has at most 9, right? And if you were graphing it, right, it would have at most 8 turns inside of the graph, right? And how do we get the turns, right? Calculus 1. All right. Yeah. I mean, we ain't got the time though, but I got y'all for next semester if y'all want. Yeah. Mm-hmm. But there's more to it. There's more to it. We'll get there. We'll get there. Yeah. All right. So check this out. So moving on. The revenue in millions of dollars for a fictional cable company from 2006 through 2013 is shown. So we got the years 2006, 7, all the way to 13, and we got the revenue that it made, right? 52.4, 52.8, etc. Right? All the way down to 14.7. The revenue can be modeled by this polynomial function for revenue. R of t is equal to negative 0.037 t to the fourth, right? Plus 1.414 t to the third minus 19.77 t squared, etc. You guys can see it, all right? Where R represents the revenue in millions of dollars and T represents the year, right? So because all of the years are 2000, etc., right? You could just do T6, 7, 8, etc. You get what it means, right? Um, with T equals 6 corresponding to 2006, for example, over which intervals is the revenue of the company increasing and over which intervals is the revenue of the company decreasing? These questions, along with many others, can be answered by examining the graph of the polynomial function. We have already explored the local behavior of quadratics, a special case of polynomials, right? In this section, we'll explore the local behavior of polynomials in general, right? So what's happening inside that graph, right? It's about to be lit. I'll give y'all the sauce right now. All right. So we're going to be recognizing characteristics of graphs of polynomial functions, right? So polynomial functions of degree 2 or more have graphs that do not have sharp corners, all right? Recall that these types of graphs are called smooth curves, right? Polynomial functions also display graphs that have no breaks, all right? They're continuous. Curves with no breaks are called continuous. So figure 1 shows a graph that represents a polynomial and a graph that represents a function that is not a polynomial. All right. So you see how we have this smooth curve right here. All right. We could draw this with our pen. One stroke. That's all we need to make that, right? But you see this other graph over here? We have to draw this. Then we have to lift up our pen and then put it back down on the paper and then continue the drawing, right? That's not a polynomial. Right? That's some piecewise thing. Let's do an example real quick because it's about to get crazy over here, right? So we're gonna be recognizing polynomial functions right here. All right. So the question is, which one of these polynomial functions? So the first one, polynomial function or not? Yes, it is, right? Because it's smooth is good. Absolute value function, number 2, polynomial function or not? Why? We don't have to pick it up, but it has a sharp turn. That's why, right? All right. I got some more. I got some more. I got some more. Let's look at this third one. Polynomial or not? Third one. Well, this is the third one, the first one. Yeah. Polynomial? Okay, good, good. What about the fourth one? This one right here. Was it? Nope. Why not? Because it has a break in it, right? If I was drawing this, I'd have to take my pen, draw the top, take it up, then put it back on the page just to draw the bottom, right? So that's for that reason, it's not a polynomial. All right, so here's a little question. Do all polynomial functions have as their domain all real numbers? Yes, they do. It's good information, all right? So any real number is a valid input for a polynomial function. So if I give you a polynomial and I say, yo, what's the domain of it? What you gonna tell me? Exactly, right? All real numbers. Mhm. Yes, all real numbers. Very good. All right. All right. Here comes stress. It's the hard part. Nah, we ain't get there yet. Yeah. All right, so using factoring to find zeros of polynomial functions. So recall that if f is a polynomial function, the values of x for which f of x equal to 0 are called the zeros of f, right? If the equation of the polynomial function can be factored, we can set each factor equal to 0 and solve for the zeros. We can use this method to find the x-intercepts because at the x-intercepts, we find the input values when the output value is 0, right? For general polynomials, this can be a challenging prospect. While quadratics can be solved using the relatively simple quadratic formula, the corresponding formulas for cubic and fourth degree polynomials are not simple enough to remember, right? The formulas do not exist for general higher degree polynomials. Consequently, we will limit ourselves to 3 cases in this section, all right? Case 1, the polynomial can be factored using known methods, greatest common factor and trinomial factoring, right? On your formula sheet, so don't worry. I know y'all didn't learn that in 28, right? Step 2, the polynomial is given in factored form. This is our holy grail. Hallelujah, if they give it to us like that, right? Step 3, we got to use some technology, right, to determine the intercepts, right? AKA use a graphing calculator. All right. By the way, just a little commercial break. All right. So for the test tomorrow, y'all could use your calculators. All right, bring them in. If you don't have a calculator, right, you guys can actually borrow one right upstairs. They close at 5:30, just letting you know. Right. They have the TI 83 calculators up there. Just letting y'all know for free. Right? I recommend the 36X Pro, right? It's that black calculator right there. Right? It's only $20. In case y'all are interested in purchasing one. That calculator is the bomb. All of them, you know. So, huh? That you can factor? TI 83. Yeah, it's free. You just go up there with your card and boom, and they let you borrow it. I think you can borrow it for like a day, a week, or like 3 months, something weird like that, you know? Or you can go out and buy one, your choice. And again, I recommend that calculator. Um, this calculator can't graph, but it does have a table of values. And from the table, that'll set you free for all your questions, you know? And then I don't have time to go through it with each different calculator, but if you guys go to tutoring, right? I told all the tutors how to do it, how to use it, so you guys can ask them. All right. Give y'all a little bit of tea right now. All right. So given a polynomial function, f, we want to find the x-intercepts by factoring, right? Here's how you do it. Step 1, you set the whole equation equal to 0. So f of x equal to 0. Step 2, if the polynomial function is not given in factored form, factor out any common monomial factors, greatest common factor, right? Step after that, B, factor any factorial binomials or trinomials out. All right. So now we talking on some like factor by grouping if possible, that kind of thing, right? Step 3, set each factor equal to 0 and solve to find the x-intercepts. That's it. Right. Right. It's a power function. Right. So that'll be good. Yeah. All right, let's look at this. I want to find the x-intercept of this polynomial function by factoring right here. What should I do first? Somebody help me. All right, I'm going to factor out x squared, right? So this is going to be f of x is equal to x squared times what's this? X to the fourth minus 3x squared plus 2, right? Right? Now what should I do after that? Should do a little substitution, right? Let, let's say that t is equal to x squared, for example, right? What would this become? X squared. Well, no, that's technically that'll be t, no? So t times t squared minus 3t plus 2. Let's factor that out. This is t. This is going to be what? T. What's my factors? -2 and -1. Very good, right? Let's plug negative because you have to add up to -3. Yeah. Now I'm going to throw back in the x squared, just to be fair, right? So now what do I have? I have x squared times x squared minus 2 times x squared minus 1. Y'all already know what's going to happen with that x squared minus 1, difference of two perfect squares. So this is what? X squared minus 2, x plus 1, x minus 1, right? Set each one of these equal to 0. You already know. So boom. So I got x squared is equal to 0. So you already know that's x equals 0. I got x squared minus 2 equals 0. Add 2. Add 2. Right? So now I got x squared is equal to 2. There's some complex nonsense right here. Right? So plus or minus 2, something like that. Square root 2. Yeah. Yeah. Oh, just square root 2. Yeah. So x plus 1 equals 0. I'm going to subtract 1, subtract 1. X equals -1. That's x minus 1. Whoops. X minus 1 equals 0. Add 1. Add 1. X equals +1. Give me these points now. Right? So we're going to have what? What's the first one? X-intercept. 0, 0. Very good. What's these next two right here? Negative square root 2, 0. All right, and then square root 2, 0. What about this next one? 1, 0, and last one? 1 is 0. All right. 1, 2, 3, 4, 5. Oh well. It happens. Technically speaking, there's one more. There's also this one that's here as well that's hiding because we have a multiplicity of 2 on the 0, but that's just why you don't see it again. All right. So that's our 6 intercepts for this question. All right. Good time, right? Yeah, that's not too bad. If you guys want to see what this graph looks like, this is it right here. So we got our five intercepts. I did draw an extra one. right? Because it had a multiplicity, but really it's only 5 intercepts, right? And there they are. You have the negative square root 2, the negative 1, the 0. You got the positive 1 and the positive square root 2. That's it. All right? That's how the graph looks. Don't worry about the turning. You'll do that another time. All right? Let's do another example. Although you guys pretty much get the gist of what we're doing here, right? Well, let's try another example. I got f of x is equal to x cubed minus 5x squared minus x plus 5, right? So I want to find the x-intercepts here. So I'm set this equal to 0. How do I factor this?
X. Like X equal X squared, then you replace.
How many terms do I have here? So what do I do when I have 4 terms?
Alright.
Divide and conquer. All right. Factor by grouping, right? So what's the greatest common factor on the left? Perfect, x squared, right? And what's left over? X minus 5, right? What about the left-hand side, right? I mean, the right-hand side, excuse me. What do they have in common? Negative x plus 5.
They got, X,
Not x.
which one? Negative.
The right-hand side, the negative x plus 5. What do they have in common? Not just one, they have
Negative.
negative 1, right? Negative 1. So it's like you're dividing by negative 1, right? This is negative 1. So what's left over? X minus 5. Good. Now I have the same thing, right? So we're going to factor that out. So we should have 0. This is going to be x minus 5 and x squared minus 1. But you know, that's the difference of 2 perfect squares, right? So let's go a step further. So this is 0 is equal to x minus 5, x plus 1, x minus 1. All right? And then you already know, set them all equal to 0. X minus 5 equals 0 plus 5 plus 5. X1 is equal to 5. X plus 1 equals 0. Subtract 1, subtract 1. X equals negative 1. X minus 1 equals 0. Add 1, add 1. So x equals positive 1. What's the points? Tell me. 5 comma 0. What else? 1 comma 0. What's the last one? Perfect, perfect. Those are my x-intercepts. We're done. Questions on this? All right. Don't worry, it's all on your formula sheet. When you're doing your homework and you're looking at it, like, oh, which one can I use? Huh? Good times, good times, good times. All right, this is a little bit easier. I'm asking you the same thing though. Give me the y-intercepts, give me the x-intercepts. Y'all want to start with the x's first? All right. So 0 is equal to x minus 2 squared times 2x plus 3. Tell me what to do. Uh-huh. So I have x minus 2 squared equals 0, and then I have my 2x. Hold on, I made a mistake. I have my 2x plus 3 equals 0. Let's just solve for them, right? I'm going to square root both sides, which you do to one side, you do to the other. So I have x minus 2 is equal to 0. Add 2, So I'm gonna have what? X equals 2. Over here, I'm going to subtract 3. What I do to one side, do to the other. So now I have 2x is equal to -3. Divide by 2, or we do to one side, do to the other. So I have x is equal to -3 over 2. All right. So now, what's my points? 2 comma 0. What's the other one? Perfect, perfect, perfect. What about my y-intercept? How do I do that again? I forgot. Right? Make x 0, so g of 0. So this is 0 minus 2 squared times 2 times 0 plus 3, right? So what's that, like -2 squared? What's that, like 4 times 3? What's 4 times 3? I don't know my timetables. 12. Appreciate that. What's the point though? Very good. And that's it. That's my y-intercept. X-intercepts. Right? Now you might notice something though, right? If I was actually to multiply this out, blah, 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 right? My leading term would be of what degree? Not 6. It would be what degree? What degree would this? Not 2. If I was to multiply everything out, what would my leading term be? Not the coefficient. I'm asking about the power, the degree. What degree would it be? To the third power, right? So that means that this answer has at most 3 roots, right? We only found 2 roots, right? Why is that? Because the 2 comma 0, right, has a multiplicity of 2. That's what that square is. X minus 2 squared. All right? Just letting y'all know that. In case you were wondering, like, yo, shouldn't there be 3 roots? Like, nah. That's safe. Thanks, thanks. I don't know if you guys want to see the graph for this. So this is how this would look. Little analysis real quick. 1 second. Like if y'all did it on y'all calculator, this is how it would come out right here. Right? Couple of points to talk about. So remember we had -3 over 2. That's the same thing as -1.5. That's it right here. That's my x-intercept. I also have my 2 comma 0. That's my other x-intercept. And my y-intercept is 0 comma 12 right there. And that's how it looks. We said that it was going to be to the 3rd degree. So bless you, bless you. So you already know how the end behavior is going, right? You're going to be down and then up. Okay. It's positive and it's odd powered. This is an example more so for the future, but I'm going to share it with you guys. So this is the same kind of problem, right? I want the x-intercepts and I want the y-intercept, right? We could tell what the y-intercept is. This is not too bad, right? So h of 0 is just what? 0 plus 0 plus 0 minus 6, right? So this equals -6. So my point is what? 0, -6. Perfect, right? That's the y-intercept. But for the x-intercept, this is not easily factorable, right? Grouping doesn't work for this, right? Because look, if I group the first 2 together, right, and then I factor out the x squared, I'm going to have x squared times x plus 4. But on the right-hand side, I'm going to have, what, just 1 times x minus 6. They're not the same, right? So this is not easily factorable, right? So for this example, you would need to use the graphing calculator, right? Or a calculator technology to find the intercepts, all right? If I was using your calculator, for example, I would put it in and I would look at the table values, right? And you might notice some numbers are negative, some numbers are positive. When you see a number that goes from negative to positive, in between there, there's a zero, right? Or if you see a number go from positive to negative, in between there, there's a zero. Or if you use a graphing calculator, right? Let me show you. If you use a graphing calculator, you'll get a graph that looks like this. Huh? Yeah. It's not easily factorable, this one. It can be done, right? Like we have like formulas that we could use with it, but it's not easily factorable. But this is what the graph would look like, right? And if you were using your calculator, you would want to know what are these intercept points, right? And those would be the x-intercepts, so they're -3, -2, and 1, right? If you were looking at the table of values, you'd be able to see that, right? You would see, let's go from left to right, right? So you would see the numbers are negative, and all of a sudden they start turning positive. So they just cross the zero right there. Then you would see the numbers go from positive back to negative, right? So obviously in the table, they cross the zero at that point. And then over here, keep going, you're going to notice that the numbers go from negative to all of a sudden they're all positive. It crossed the zero at some point, right? Now these are nice numbers, -3, -2, 1. You would easily be able to tell them just from going up or down the graph. I mean the table, I meant to say, excuse me, right? If you have a graphing calculator, you can actually trace it. There's a function in there called trace, and then you can find the x-intercepts that way, right? That one works. That one could do this. Yeah. You just type in the function and then you look at the table of values and you would see how the numbers change over time. Mhm. Uh-huh. X plus 4? How you get that? But I can't though, because I don't have x squared from everything. Oh, you mean if I group them, you're talking about? Yeah. But remember, in the parentheses, they gotta match. Like when I do the greatest common factor on both sides, they have to have the same parenthesis match, and then I could finish the grouping thing. But this doesn't do that because if I factor out the x squared, I'm left with x plus 4, and on the other side, I'm gonna factor out 1. I'm left with x minus 6, which is not the same. So it won't work. Yeah. All right. Y'all get the idea with the calculator. So I'm gonna move on to another topic, right? Identifying zeros and their multiplicities, right? So we saw this before. You heard me mention that word before, multiplicity, right? So graphs have differently, excuse me, graphs behave differently at various x-intercepts. Sometimes the graph will cross over the horizontal axis at an intercept. Other times the graph will touch the horizontal axis and bounce off. So for example, we have this function here, x plus 3 times x minus 2 squared times x plus 1 cubed. Notice in the figure, right, this is the graph for that function right there, right? That the behavior of the function at each of the x-intercepts is different, right? So look at this first one, x plus 3, right? I have just one of them. What did it do? It passed through the x-axis. You notice that, right? Then let's look at this other one, x minus 2 squared. Remember, that's going to be positive 2, right? What did this do? This touched, right? It touched the x-axis, and then it just went up to infinity, right? And then I have x plus 1 cubed, right? X plus 1 cubed. What did that do? It also passed through the x-axis, right? But it did it in like a x cubed kind of style, where like it was like negative infinity, then came into 0, then it went to positive infinity, right? Okay. Just an observation. Just an observation there.
So,
Hmm?
by working with the function step by step,
Say it again.
by working with the function step by step.
It is. Yeah, that's the reason why. Mhm. So the x-intercept of -3 is the solution of the equation x plus 3 is equal to 0. The graph passes directly through the x-intercept at x equals -3. The factor is linear and has degree of 1, right? So there's only one x plus 3. So the behavior near the intercept is like that of a line. It passes directly through the intercept, right? So we call this a single zero because the 0 corresponds to a single factor of the function, right? The x-intercept 2 is a repeated solution, right? It's x minus 2 squared equals 0. The graph touches the axis at the intercept and changes direction, much like x squared would do, right? The factor is quadratic, degree 2, so the behavior near the intercept is like that of a quadratic. It bounces off the horizontal axis at the intercept, right? The factor, right, is repeated. That is the factor x minus 2 appears twice. The number of times a given factor appears in a factored form of the equation of a polynomial is called the multiplicity, right? It's called multiplicity. So the 0 associated with this factor is x equals 2. The multiplicity 2 because the factor x minus 2 occurs twice, all right? Now let's talk about the 1. The x-intercept -1 is the repeated solution of factor x plus 1 cubed equals 0. The graph passes through the axis at the intercept, but flattens out a bit first, right? This factor is cubic, degree 3, right? So the behavior near the intercept is like that of the cubic function, right? With the same S shape near the intercept as a toolkit function f of x is equal to x cubed. We call this a triple zero or a 0 with multiplicity of 3. All right. This is cool stuff here. Cool stuff. All right. So check this out. This is the sauce right here. This is sauce. So for zeros with even multiplicities, the graph touches or are tangent to the x-axis, right? For zeros with odd multiplicities, the graph crosses or intersects the x-axis, right? So even multiplicity, it's going to touch. Odd multiplicity, we going through it, right? Or we're going to intersect it, whatever you want to call it, right? So here's some examples right here. Multiplicity 1, right? Single 0, we're going straight through the x-axis like a line, right? 0 with multiplicity 2, right? We're gonna bounce, right? We're gonna touch it and then we're gonna bounce right off, right? 0 with multiplicity 3, we're gonna go up to it, we're gonna flatten out a little bit, then we're gonna keep going, right? So that's how we doing it. For higher even powers such as 4, 6, 8, right? The graph will still touch and bounce off the horizontal axis, but for each increasing even power, the graph will appear flatter as it approaches and leaves the x-axis, right? For higher odd powers, right, such as 5, 7, 9, the graph will still cross the horizontal axis, but in each increasing odd power, the graph will appear flatter as it approaches and leaves the x-axis. All right? This is the sauce right here. All right? Let me give y'all a little definition real quick. Just trying to sum it up real nice and easy. All right? So graphical behavior of polynomials at x-intercepts. If a polynomial contains a factor of the form x minus h to the p power, for example, right? The behavior near the x-intercept h is determined by the power of p, right? So we say that x equal h has a zero of multiplicity p, right? The graph of a polynomial function will touch the x-axis at zeros with even multiplicities. All right. Then they're going to bounce. The graph will cross the x-axis at zeros with odd multiplicities. Right. We're going to cross at odd. All right. One is odd. That's why it crosses, if you're wondering. All right. The sum of the multiplicities is a degree of the polynomial function. All right. Sum of the multiplicity is the degree of the polynomial function. Low key, you guys knew that already. You just never heard it in that, heard it said that way. No? So let me give you a little T. All right. So given a graph of a polynomial function of degree n, we want to identify the zeros and their multiplicities, right? So here's how you do it. Step one, if the graph crosses the x-axis and appears almost linear at the intercept, it has a single zero at that point. If the graph touches the x-axis and bounces off the x-axis, it has a zero with an even multiplicity at that point, right? If the graph crosses the x-axis at zero, right, it has an odd multiplicity, right? And then the sum of the multiplicities is going to be less than or equal to n, right? And remember, that's because the factors of the polynomial, right, it has at most n factors, right? So less than or equal to n. Let's look at an example. Hmm? Yeah,
Financial aid, financial aid, so just excuse me, we don't see.
I got you. Yeah, just come through. Just come through.
Yeah,
Yeah.
know how that goes.
Yeah.
Even
Even if it,
I drop out, they trying to like give me credit for it, and I'm like, nah, yeah, take a look at that. So basically,
Right.
it's you, and I'm like,
got you. All right, I got you. Just keep showing up. It's all right. Yeah, it's no worries. Yeah, it's no worries. Yeah. Yeah. All right, look at this. Identifying zeros and their multiplicities, right? So use the graph of the function of degree 6. This is degree 6, right? And you want to identify the zeros of the function and their possible multiplicities, right? So real quick, this is easy to find the zeros right here, right? Let me get my yellow highlighter right here, right? So I got a 0 right here. I'm looking at where it's touching the x-axis. I got a 0 right here. I got a 0 right here, and I got a 0 right here. Technically, I have a 0 right here just to make it feel good. I'll highlight it, right? So I have 6 possible roots, right? This one, the -3 right here, right? I'm gonna just write on this side. So -3, is that gonna have a odd multiplicity or even multiplicity? What do we think? I'm looking at -3 right here. Even, right? So it's gonna have an even multiplicity. I don't know what it is. I don't know if it's 2, 4, 6, 8, but all I know is that it's even, right? What about the -1? Right? So I'm looking at -1, which is right here. Even or odd? We pass through the x-axis, right? So what does that mean? No, not neither. We're passing through the x-axis, so it's going to be what? Odd, right? So this is odd multiplicity. I can't spell that word, but y'all get the idea, right? What about 4? What about positive 4? Even or odd? We're passing through it. Odd, right? Odd multiplicity.
And the odds, so,
Mhm.
like,
Right. Right. Now, I don't know what the multiplicities are. All I can tell you is that this is a polynomial of degree 6, right? So whatever these even and odd multiplicities are, they have to add up to at most 6. They can have at most 6 factors. All right. That's that. Feel like we get the gist of that. Let's take a look. So now we want to talk about determining end behavior, right? So as we have already learned, the behavior of the graph of a polynomial function of the form f of x is equal to a n x to the n plus a n minus 1 x to the n minus 1, etc., right? Will either ultimately rise or fall as x increases without bound, and will either rise or fall as x decreases without bound. This is because for very large inputs, say 100 or 1000, the leading term dominates the size of the output, right? The same is true for very small outputs like negative 100 or negative 1000, right? Recall that we call this behavior the end behavior of the function, as we pointed out when discussing quadratic equations. When the leading term of the polynomial function a n x to the n is an even power function, as x increases or decreases without bound, f of x increases without bound. When the leading term is an odd power function, as x decreases without bound, f of x also decreases without bound. As x increases without bound, f of x also increases without bound. If the leading term is negative, it will change the direction of the end behavior, right? And we kind of know this already, just a little bit of a review. All right. Just giving y'all this information, and y'all be able to use it. So for an even degree, this is like kind of what I was telling you how I would like the answers, right? So for a positive leading coefficient, a n greater than 0, the end behavior will be like that, right? So as x is going to positive infinity, the f of x is going to infinity, and as x is going to negative infinity, the f of x is going to positive infinity, right? For a positive leading coefficient, a n is greater than 0, right? But it's odd. It's an odd degree, right? So we're gonna have, as x is going to negative infinity, right? We're gonna be going down, and then as x is going to positive infinity, we're gonna be going up, right? And then the new thing it was showing you, it's not really new, but you guys get the idea, all right? Make that a little bit bigger. So for a negative leading coefficient, right? A n less than 0, right? We're gonna reflect over the x-axis, right? And we're going to be going down. So as x is going to negative infinity, we're going to negative infinity. As x is going to positive infinity, we're going to negative infinity, right? When the coefficient in front is negative, right? for an odd function, right? When the coefficient is negative, right? As x goes to negative infinity, we're going to be going to positive infinity. And as x is going to positive infinity, we're going to be going down to negative infinity. All right. This is just like a slight little review. You know, we already took a look at that. All right. I have a little bit more left, but I understand it is time. So if y'all have to run, go ahead. Y'all can catch the rest on the recording. All right. So understanding the relationship between the degree and the turning points. All right. So in addition to the end behavior, recall that we can analyze a polynomial function's local behavior. It may have a turning point where the graph changes from increasing to decreasing, rising to falling, or decreasing to increasing, falling to rising. So we look at the graph right here, this polynomial. This is f of x equal to x to the fourth minus x to the third minus 4x squared plus 4x, right? The graph has 3 turning points, right? So more specifically, the turning points that we're talking about are like here and here and here, right? So we're going from decreasing to increasing, then decreasing to increasing, all right? Fun stuff. All right. So this function f is a 4th degree polynomial function and has 3 turning points. The maximum number of turning points of a polynomial function is always 1 less than the degree of the function. Remember that. All right. For calculus. So just want to interpret the turning points a little bit. Again, I'm just mentioning it. I'm not going to ask you to do it. So a turning point is a point of the graph where the graph changes from increasing to decreasing, rising to falling, or decreasing to increasing, falling to rising. A polynomial n will have at most n minus 1 turning points. All right. So let's just say I had a polynomial. It had degree 5. What's the most amount of turning points that it could have?
4.
4. All right. Y'all get the idea.
I'm trying to get it. You look at like the where you have before.
Mm-hmm.
The fact that there's powers involved.
Right.
Some kind of third.
Exactly.
But at the end of the equation, there is no power.
Right.
90 plus 15 or plus.
Right. Exactly.
Multiply by 4.
Exactly. That's it.
Every time you see like power, that means it's good.
Right. Exactly. All right, last topic, right? We're going to be graphing polynomial functions, right? So we can use what we've learned about multiplicities and behaviors and turning points to sketch graphs of the polynomial functions, right? So let's put it all together, right? And look at steps required to graph a polynomial function. Right? So here's a T, right? How to. Given a polynomial function, we want to sketch the graph. Here's how we do it. Step 1, you find the intercepts, y-intercept, x-intercept, plot them points, pop, right? Check for symmetry, right? If the function is an even function, its graph is symmetric about the y-axis, right? That is, if f of negative x is equal to f of x, right? If the function is an odd function, its graph is symmetric about the origin. That is, if f of negative x is equal to negative f of x, right? Use the multiplicities of the zeros to determine the behavior of the polynomial at all of the x-intercepts, right? So if there's a odd multiplicity, you know what's happening. We're going straight through that x-intercept. If it's an even multiplicity, you know what's happening. We're bouncing off of that x-intercept, right? Determine the end behavior by examining the leading coefficient, right? The leading term. So if the leading term is even, you already know we going up, right? If the coefficient in front is positive. If it's negative, right? Assume not negative. If it's odd, right? We're gonna be going down and going up on one, right? And if it was negative, we switch that. All right. Use the end behavior and the behavior of the intercepts to sketch the graph. Ensure that the number of turning points does not exceed, right, one less than the degree of the polynomial. And then, of course, you can always use the calculator to check your answer. All right. So that's how we do the graphs right there. And we could call it at that.
I don't know.
Yeah.
Think about the sketch,
Uh-huh.
if, you like hypothetically break down each term
Mm-hmm.
as its own function.
Right.
So, you know, the i's power that is, you know, x squared. You gotta know that there's this shape, and then, oh, well, it's out there x squared, though, it might be, you know.
X to the fourth or X to the fifth, right?
That
Exactly. Mm-hmm.
kind of goes on, it's showing us the beginning of the different types of glass.
Exactly. That's what this is. That's exactly what this is. All right. So that's it. Any questions about this topic? Let's see. All right. All right. So I'm gonna stop right there. Everybody online, have a good night. Um, the homework for this